Most welcome to 1255, and this is the view of Gothenburg facing southeast. To the right you see the amusement park Liseberg, and to the left the Gothenburg World Trade Center. We also have cabins for construction. Gothenburg is presently involved in its most extensive rebuilding project ever, called the West Link. They are blowing up the mountain to make a tunnel aid communication for the whole town. They are taking care of the whole town as a unity. This is not what we're doing with the universe. It is not a unity. It is not a universe. It is a multiverse. I will continue with a book by Roberto Unger and Lee Smolin. Presently at page 100 and what could it be? 129, I think it is. No such antipathy opposes the combination of the ideas of the singular existence of the universe and of non-cyclic succession to cosmological inflation, as distinguished from eternal inflation. Assume for the sake of this argument that the conjecture of the super rapid initial expansion of the universe may be vindicated by conclusive inference from observable remnants of the very early universe. Cosmological inflation, in such a view, represents the immediate aftermath of a superdense and super hot moment. In the course of the events of which it formed part, causal continuity was never entirely broken. The values of the parameters, although extreme, never became infinite. If causal continuity remained uninterrupted, the presumption of science is that it continued indefinitely back into the past. We subtract nothing from our present ignorance of that past by resorting to the speculation of the existence of a vast or infinite array of other universes. We merely provide ourselves a pretext to stop looking and to seek in mathematics what we have so far failed to find in nature. Inflation fails to contradict non-cyclic succession proposed against the background of the idea that there is one causally connected universe at the time. Eternal inflation does contradict it. It contradicts it insofar as theories of eternal inflation reenact part of the intellectual program of steady-state theories in cosmology. A changeless cosmological process going on forever and ceaselessly re-establishing the conditions for its own continuance. It contradicts it even more to the extent that eternal inflation is married to the multiverse idea. The product of this marriage is the conjecture of an infinity of unobservable pocket universes generated by eternal inflation. The contradiction is only mildly attenuated in variants of eternal inflation theory that depict inflation as eternal into the future, but not into the past. According to the view that under reasonable assumptions, the inflating region must be incomplete in past directions. Although it is common to suppose that the idea of eternal inflation represents a natural extension of the conjecture of cosmological inflation, it has a wholly different character, especially when associated with the conception of a multiverse. It evokes the picture of a recurrent process governed by immutable laws. It eludes empirical confirmation or falsification. It justifies its recalcitrance to empirical challenge by its appeal to what we here argue to be a misguided view of the relation of mathematics to nature and of the place of mathematics in science. In certain respects, it shares the spirit of theories of cyclic succession. As they do, it teaches that the most important facts about nature, those that regard its basic structure and fundamental regularities, never change. The thesis of the singular existence of the universe, as developed by the conjecture of non-cyclic succession, is compatible with cosmological inflation. It cannot be reconciled with eternal inflation. Rather than being a flaw, this incompatibility amounts to a virtue. It defines one of several ways in which that thesis can be put to the test. Any evidence for eternal inflation, if, as its proponents claim, there can be such evidence, amounts to evidence against the twin ideas of the singular existence of the universe and of the historical non-cyclic succession of universes or of states of the universe. 5. The argument from rejection of the second cosmological fallacy. The ideas of the singular existence of the universe and of non-cyclic succession enable us to begin making sense of the emergence in the course of the history of the universe, both of fundamental structures or constituents of nature and of law-like regularities in the interactions of these constituents. The now standard Big Bang cosmological model has been immensely successful in providing a framework within which to understand what has already been discovered about the history of the universe. This model suffers, however, from two basic weaknesses. One frailty is the continuing reliance of its proponents on the metaphysical element in the theory of general relativity. The representation of time as an aspect of a space-time continuum, described as a four-dimensional, semi-Riemannian manifold that can be arbitrarily sliced by an infinite number of space-time coordinates. I argue in chapter 4 that Riemannian space-time, with its exclusion of preferred cosmic time, its denial of the fundamental non-emergent character of time and its consequent treatment of time as an accessory incident, together with space to the disposition of matter and motion in the universe, represents a philosophical gloss on the empirical hardcore of general relativity. I go on to argue that the metaphysical conception of such a space-time continuum inhibits, very important, inhibits our understanding of what has already been discovered, as well as our openness to what may yet be discovered about the history of the universe. Another weakness of the way in which the standard cosmological model has developed concerns its picture of events in the very earliest universe. so long as these events remain hidden behind the screen of the infinite, an infinite initial singularity mistaken for an account of physical events rather than recognized as a mathematical notion indicating limits to the applicability of the physical theory. We cannot hope to progress in our understanding of those events. It is only when we begin to represent the earliest history of the universe as a condition in which temperature and density had extreme but nevertheless finite values, that we can hope to subject it to physical reasoning and to lay it open, at least in principle, to empirical inquiry. In so doing, we satisfy the basic condition for causal continuity between our universe and any universe that may have preceded it, or between the expanding and contracting of the one real universe over time. Let's take this. In doing so, and this is incredibly important, we satisfy the basic condition for causal continuity between our universe and any universe that may have preceded it, or between the expanding and contracting of the one real universe over time. The idea of succession then arises as the alternative both to the stability and eternity of the universe, as in the steady-state cosmology of the early 20th century, and to the conception of an absolute beginning of the universe out of nothing. Succession requires much less of a break than do its rival conceptions, not only with what we already know about the history of the cool-down universe in which we find ourselves, but also more generally with what we know about how nature works in the many domains studied by the specialized sciences. Up to this point in the analysis, there is no reason to prefer either a cyclic or a non-cyclic view of succession. Both can accommodate causal continuity, make sense of the fiery beginnings of the present universe, and avoid the appeal to the mathematical conceit of the infinite, or to the making of something out of nothing. The different implications and unequal advantages of cyclic and non-cyclic views of succession begin to become clear when we consider the problem of emergence of the basic structure of the universe. We already know enough to conclude that chemistry, as described by the periodic table, could not have existed in the earliest moments of the history of the universe. Research conducted under the guidance of the now standard cosmological model also gives increasing grounds to infer that the elementary constituents of nature, as described by the similarly successful standard model of particle physics, could also not have existed, at least not in their present form, very early in the history of the universe. The fundamental structure of nature as we as we observe it in the cool down universe has a history. Each of its pieces emerged in the course of this history. The plasma existing at the beginning of the universe did not resemble the rudimentary structure portrayed, but not historically explained by the standard model of particle physics. There is no evidence that the standard model of particle physics describes conditions prior to nucleosynthesis. Something to think about. There are two distinct sets of reasons for the difficulty that we experience in developing a historical account of the step-by-step emergence of this structure. First reason is that even after we throw down the principal bar to empirical research represented by the notion of an infinite initial singularity, we continue to lack the experimental means with which to simulate conditions in that earliest history. Temperature was at that time higher than the energies generated in our present particle colliders. There is, however, no reason of principle, why we cannot hope to develop means for investigating those conditions in the future. A second reason is that a gap remains between our understanding of the laws, symmetries, and constants in the earliest history of the universe. And the evolution resulting in the fundamental structure that we observe. The regularities of nature that we register and the astonishing stability of which in the cool down universe we cannot fail to acknowledge, may be incompatible, may be compatible with the changes producing this structure. They fail, however, to explain it. They are the regularities governing the regime forged in the early history of the universe. They do not, however, account for either the emergence of this regime or consequently for themselves. This gap confronts us with a choice between two modes of thoughts according to the way of thinking characteristic of the tradition of physics inaugurated by Galileo and Newton. The regularities must have been already and always there, as eternal and unmoved bystanders, rather than as temporal and shaped participants. In the history of the universe. It is a view that not only circumscribes the reach of history and of time, but also violates the principles of reciprocated action. Yeah, that's true actually. we imagine that part of nature, the laws, symmetries, and constants, acts without being acted upon. They fail to explain themselves, the distinctive and even finely tuned content of the laws, symmetries, and constants, which we are unable to deduce from any more general rational necessity, remains mysterious. This approach gains its semblance of plausibility from the undisputed stability of the laws, symmetries, and constants in the cool-down universe. However, it could not understand these stable regularities to be eternal if it failed to make as well two other moves. The first move is to treat the stable forms that nature takes in the consolidated, though evolving universe as its permanent canon of forms. This is the second cosmological fallacy to be remembered. The second move is to make the idea of immutable laws, symmetries, and constant to be an indispensable prerequisite of scientific explanation. Neither of these moves is justified. Neither. Zero. Zilch. The objection to the first move is that we may have reason to infer that nature in the early universe, as well as in extreme states of its later history, must have been and must be organized in a different way from the way in which we see it organized now. What remains open is whether any part of the fundamental order of nature, that is to say, its elementary fields and particles as described by the standard model of particle physics, existed then as it came to exist later. The safest assumption and the most compatible with the direction of our discoveries about the history of the universe is that none of it was then what it is now. The objection to the second move is that unstinting recognition of the mutability of nature in all of its elements need not undermine our powers of causal explanation. That it need not do so is shown by the explanatory practice of the life and earth sciences, as well as by the more remote lessons of social and historical study. To recognize the force of these objections is to open the way to another mode of thought. According to this alternative, the structure of nature and its regularities evolve jointly. Indeed, causal connections, rather than being instances of immutable laws of nature, constitute primitive features of nature. Although we are accustomed to see them display recurrent and general form in the observed universe, they may exhibit no such law-like character in extreme states of nature. Among such extreme states are those that seem likely to have prevailed in the earliest history of the present universe. The conception of plurality of divergent universes, the multiverse, each with its own distinctive regularities and structures, loosely subsumed under the ideas of a physical view, such as string theory, cannot help make sense of these problems. On the contrary, it simply multiplies the enigma by as many universes as it postulates. For in each of these universes, the fundamental structure and the regularities must have come from somewhere through a physical mechanism that conceit of the mathematical possibility fails to explain or even to describe. Moreover, in each of these postulated universes, if we understand them by analogy to our own, and in parenthesis, speaking about parenthesis, and how else can we understand them, given that they are forever inaccessible to us? The distinct fundamental structure may have been different at the outset. Consequently, for each of them, the same question arises: to what we imagine the regularities were doing when the states of affairs that they supposedly govern did not yet exist. Only the idea of a singular universe placed in a historical context that makes room for a succession of universes or of states of the universe can enable us to address these issues, and to do so in a fashion that remains, at least in principle, open to empirical study In this respect, the non-cyclic view of succession enjoys a decisive advantage over the cyclic one. Under the cyclic account of succession, both the fundamental structure of nature and its laws, symmetries and constants remain the same. Then there is no prospect of explaining what came later by what came before. If it is admitted that in each formative moment of a new universe, the basic constituents of nature re-emerge, they must, under this conception, always cluster into the same natural kinds and conform to the same regularities. For such an account to be complete, the regularities of nature that it identifies must explain by what mechanisms the same structures repeatedly re-emerge of each formative moment of each succeeding universe. It is true that we can mount computer simulations encoding our present understanding of the laws of nature that simulate the evolution of the universe back to relatively early stages. What we cannot do, however, is to reverse engineer such as a formative process beyond, or before the moment when the basic constituents described by the standard model of particle physics existed. The cyclic views of succession are in no better position in this respect than is this application of the standard model of particle physics to the early universe. They simply extend the same riddle back into the eternity of a time without transformation. If then, as I argue in chapter 4, time is the change of change, they equivocate about the reality of time. Moreover, they require for these prior universes an explanation of the recurrent genesis of structure that we do not possess even for our own universe or for its present state. I'll put a pause there and I'll continue with another text here. I'll make sort of a half summary. And this is an article by Lee Smolin from Scientific American, published in January of 2004. You can find the article starting from page 66 in the article. It's a sort of a summation and I think it could be perfect moment to put it in here, since 136, even 136 pages of the book has passed. It's actually almost 1/4. No, it is 1/4. And a bit more. I think this would aid. It's written in a more lucid style since it's from a magazine. You will also learn about something called loop quantum gravity, which is very interesting from the abstract. We perceive space and time to be continuous, but if the amazing theory of loop quantum gravity is correct, they actually come in discrete pieces. A little more than 100 years, most people and most scientists thought of matter as continuous. Although since ancient times, some philosophers and scientists had speculated that if matter were broken up in small enough bits, it might turn out to be made of very tiny atoms. Few thought the existence of atoms could ever be proved. Today we have imaged individual atoms and have studied the particles that compose them. The granularity of matter is all news. In recent decades, physicists and mathematicians have asked if space is also made of discrete pieces. Is it continuous, as we learn in school, or is it more like a piece of cloth woven out of individual fibers? If we could probe to size scales that were small enough, would we see atoms of space? Irreducible pieces of volume that cannot be broken into anything smaller. And what about time? Does nature change continuously, or does the world evolve in a series of very tiny steps, acting more like a digital computer. The past 16 years have seen some great progress on these questions. A theory with the strange name of loop quantum gravity predicts that space and time are indeed made of discrete pieces. The picture revealed by calculations carried out within the framework of this theory is both simple and beautiful. The theory has deepened our understanding of puzzling phenomena having to do with black holes and the Big Bang. Best of all, it is testable. It makes predictions for experiments that can be done in the near future that will enable us to detect the atoms of space if they are really there. Quanta. My colleagues and I developed the theory of loop quantum gravity while struggling with a long-standing problem in physics. Is it possible to develop a quantum theory of gravity? To explain why this is an important question and what it has to do with the granularity of space and time, I must first say a bit about quantum theory and the theory of gravity. The theory of quantum mechanics was formulated in the first quarter of the 20th century. A development that was closely connected with the confirmation that matter is made of atoms. The equations of quantum mechanics require that certain quantities, such as the energy of an atom, can come only in specific discrete units. Quantum theory successfully predicts the properties and behavior of atoms and the elementary particles and forces that compose them. No theory in the history of science has been more successful than quantum theory. It underlies our understanding of chemistry, atomic and subatomic physics, electronics, and even biology. In the same decades that quantum mechanics was being formulated, Albert Einstein constructed his general theory of relativity, which is a theory of gravity. In his theory, the gravitational forces arises as a consequence of space and time, which together form spacetime, being curved by the presence of matter. A loose analogy is that of a bowling ball placed on a rubber sheet with a marble that is rolling around nearby. The balls could represent the sun and the earth, and the sheet is space. The bowling ball creates a deep indentation in the rubber sheet, and the slope of this indentation causes the marble to be deflected toward the larger ball, as if some force, gravity, were pulling it in that direction. Similarly, any piece of matter or concentration of energy distorts the geometry of space-time, causing other particles and light rays to be deflected toward it, a phenomenon we call gravity. Quantum theory and Einstein's theory of general relativity separately have each been fantastically well confirmed by experiment. But no experiment has explored the regime where both theories predict significant effects. The problem is that quantum effects are most prominent at small scales, whereas general relativistic effects require large masses, so it takes extraordinary circumstances to combine both conditions. Allied with this hole in the experimental data is a huge conceptual problem. Einstein's theory of general relativity is thoroughly classical or non-quantum. For physics as a whole to be logically consistent, there has to be a theory that somehow unites quantum mechanics and general relativity. The long sought after theory is called quantum gravity, because general relativity deals in the geometry of space-time. A quantum theory of gravity will in addition be a quantum theory of space-time. Physicists have developed a considerable collection of mathematical procedures for turning a classical theory into a quantum one. Many theoretical physicists and mathematicians have worked on applying those standard techniques to general relativity. Early results were discouraging. Calculations carried out in the 1960s and 1970s seem to show that quantum theory and general relativity could not be successfully combined. Consequently, something fundamentally new seemed to be required, such as additional postulates or principles not included in quantum theory and general relativity, or new particles or fields or new entities of some kind, perhaps with the right addition or a new mathematical structure. A quantum-like theory could be developed that would successfully approximate general relativity in the non-quantum regime. To avoid spoiling the successful predictions of quantum theory and general relativity, the exotica contained in the full theory would remain hidden from experiments, except in the extraordinary circumstances where both quantum theory and general relativity are expected to have large effects. Many different approaches along these lines have been tried, with names such as twistor theory, non-commutative geometry, and supergravity. An approach that is very popular with physicists is string theory, which postulates that space has 6 or 7 dimensions, all so far completely unobserved. In addition to the 3 that we are familiar with. String theory also predicts the existence of great many new elementary particles and forces for which there is so far no observable evidence. Some researchers believe that string theory is subsumed in a theory called M-theory. But unfortunately, no precise definition of this conjectured theory has ever been given. Thus, many physicists and mathematicians are convinced that alternatives must be studied. Our loop quantum gravity theory is the best developed alternative. A big loophole. In the mid-1980s, a few of us, including Abhay Ashtekar, now at Pennsylvania State University, Ted Jacobson of the University of Maryland, and Carlo Rovelli, now at the University of the Mediterranean in Marseille, decided to re-examine the question of whether quantum mechanics could be combined consistently with general relativity using the standard techniques. We know that the negative results from the 1970s had an important loophole. Those calculations assume that the geometry of space is continuous and smooth, no matter how minutely we examined it, just as people had expected matter to be before the discovery of atoms. Some of our teachers and mentors had pointed out that this assumption was wrong. The old calculations would not be reliable. So we begin searching for a way to do calculations without assuming that space is smooth and continuous. We insisted on not making any assumptions beyond the experimentally well-tested principles of general relativity and quantum theory. In particular, we kept two key principles of general relativity at the heart of our calculations. The first is known as background independence. This principle says that the geometry of space-time is not fixed. Instead, the geometry is an evolving dynamical quantity. To find the geometry, one has to solve certain equations that include all the effects of matter and energy. Incidentally, string theory as currently formulated is not background independent. The equations describing the strings are set up in a predetermined classical space-time. That I did not know or realize. The second principle, known by the imposing name diffeomorphism invariance, is closely related to background independence. The principle implies that, unlike theories prior to general relativity, one is free to choose any set of coordinates to map space-time and express the equations. A point in space-time is defined only by what physically happens at it, not by its location according to some special set of coordinates. Actually, no coordinates are special. Diffeomorphism invariance is very powerful and is of fundamental importance in general relativity. By carefully combining these two principles with the standard techniques of quantum mechanics, we develop a mathematical language that allows us to do a computation to determine whether space is continuous or discrete. That calculation revealed to our delight that space is quantized. We lay the foundations for our theory of loop quantum gravity. The term loop, by the way, arises from how some computations in the theory involve small loops marked out in space-time. The calculations have been redone by a number of physicists and mathematicians using a range of methods. Over the years since, the study of loop quantum gravity has grown into a healthy field of research with many contributors around the world. Our combined efforts give us confidence in the picture of space-time I will describe. Ours is a quantum theory of structure of space-time at the smallest size scales. So to explain how the theory works, we need to consider what it predicts for a small region or volume in dealing with quantum physics. It is essential to specify precisely what physical quantities are to be measured. To do so, we consider a region somewhere that is marked out by a boundary. There is an illustration, I will try to read it. A central prediction of the loop quantum gravity theory relates to the volumes and areas. Consider a spherical shell that defines the boundary B. Of a region of space having some volume above. According to the classical physics, the volume could be any positive real number. The quantum gravity theory says, however, that there is a non-zero absolute minimum volume, and it restricts the set of larger volumes to a discrete series of numbers. Similarly, there is a non-zero minimum area and discrete series of allowed areas. The discrete spectrum of allowed quantum areas and volumes is broadly similar to the discrete quantum energy levels of a hydrogen atom. There's another diagram here. There will be a link to this paper you to print out or watch on your computer screens or laptops. And this one is called Visualizing Quantum States of Volume. Diagrams called spin networks are used by physicists who study loop quantum gravity to represent quantum states of space at a minuscule scale. Some such diagrams correspond to polyhedra-shaped volumes. For example, a cube consists of a volume enclosed within 6 square faces. The corresponding spin network has a dot or node representing the volume and 6 lines that represent the 6 faces. The complete spin network has a number at the node to indicate the cube's volume and number on each line to indicate the area of the corresponding face. Here, the volume is 8 cubic Planck lengths, and the faces are each 4 square Planck lengths. The rules of loop quantum gravity restrict the allowed volumes and areas to specific quantities. only certain combinations of numbers are allowed on the lines and nodes. If a pyramid sat on the cube's top face, the line representing that face in the spin network would connect the cube's node to the pyramid's node. The lines corresponding to the 4 exposed faces of the pyramid and the 5 exposed faces of the cube would stick out from their respective nodes. In general, in a spin network, one quantum of area is represented by a single line, whereas an area composed of many quanta is represented by many lines. Similarly, a quantum of volume is represented by one node, whereas a larger volume takes many nodes. If we have a region of space defined by a spherical shell, the volume inside the shell is given by the sum of all the enclosed nodes, and its surface area is given by the sum of all the lines that pierce it. Did you know about these things? Space is quantized, makes a huge difference. Out goes the Cartesian coordinates for good. And Galileo. The boundary may be defined by some matter, such as a cast iron shell, or it may be defined by the geometry of space-time itself, as in the event horizon of a black hole. What happens if we measure the volume of the region? What are the possible outcomes allowed by both quantum theory and diffeomorphism invariance? If the geometry of space is continuous, the region could be of any size, and the measurement result could be any positive real number. In particular, it could be as close as one wants to zero volume. But if the geometry is granular, then the measurement result can come from just a discrete set of numbers, and it cannot be smaller than a certain minimum possible volume. The question is similar to asking how much energy electrons orbiting an atomic nucleus have? Classical mechanics, let me get some coffee here. Classical mechanics predicts that an electron can possess any amounts of energy, but quantum mechanics allows only specific energies. Amounts in between those values do not occur. The difference is like that between the measure of something that flows continuously, like the 19th century conception of water, and something that can be counted, like the atoms in that water. The theory of loop quantum gravity predicts that space is like atoms. There is a discrete set of numbers that the volume measuring experiment can return. Volume comes in distinct pieces. Another quantity we can measure is the area of boundary B. Again, calculations using the theory return an unambiguous result. The area of the surface is discrete as well. In other words, space is not continuous. It comes only in a specific quantum units of area and volume. The possible values of volume and area are measured in units of a quantity called the Planck length. The length is related to the strength of gravity, the size of quanta, and the speed of light. It measures the scale at which the geometry of space is no longer continuous. The Planck length is very small. The smallest possible non-zero area is about a square Planck length. And the smallest non-zero volume is approximately a cubic Planck length. Thus, the theory predicts that there are about millions and millions of atoms of volume in every cubic centimeter of space. The quantum of volume is so tiny that there are more such quanta in a cubic centimeter than there are cubic centimeters in the visible universe. Spin networks, or should I end here? See how much we are straining into that. I guess sometimes. Spin networks. What else does our theory tell us about space-time? To start with, what do these quantum states of volume and area look like? Is space made up of a lot of little cubes or spheres? The answer is no. It is not that simple. Nevertheless, we can draw diagrams that represent the quantum states of volume and area. To those of us working in this field, these diagrams are beautiful because of their connection to an elegant branch of mathematics. To see how these diagrams work, imagine that we have a lump of space shaped like a cube. In our diagrams, we would depict this cube as a dot, which represents the volume with 6 lines sticking out, each of which represents one of the cube's faces. We have to write a number next to the dot to specify the quantity of volume. And on each line, we write a number to specify the area of the face that the line represents. Next, suppose we put a pyramid on top of the cube. These two polyhedra, which share a common face, would be depicted as 2 dots, 2 volumes, connected by one of the lines, the face that joins the 2 volumes. The cube has 5 other faces, and the pyramid has 4. It is clear how more complicated arrangements involving polyhedra other than cubes and pyramids could be depicted with these dot and line diagrams. Each polyhedron of volume becomes a dot or node, and each flat face of a polyhedron becomes a line, and the line joins the nodes in a way that the faces join the polyhedra together. Mathematicians call these lines graphs. Now, in our theory, we throw away the drawings of polyhedra and just keep the graphs. The mathematics that describes the quantum states of volume and area gives us a set of rules for how the nodes and lines can be connected and what numbers can go where in a diagram. Every quantum state corresponds to one of these graphs, and every graph that obeys the rules corresponds to a quantum state. The graphs are convenient shorthand for all the possible quantum states of space. The graphs are better representation of the quantum states than the polyhedra are. In particular, some graphs connect in strange ways that cannot be converted into a tidy picture of polyhedra. For example, whenever space is curved, the polyhedra will not fit together properly in any drawing we could do. Yet we can still easily draw a graph. Indeed, we can take a graph and from it calculate how much space is distorted, because the distortion of space is what produces gravity. This is how the diagrams form a quantum theory of gravity. I have to continue with the other one. See here how this completely undermines the underlying frame of reference for everything, in time and in space. Because now the frame is not continuous, it is discrete. Both the model and what it depicts have to follow discrete units. There cannot be any absolute projection. Both model and what it models are under the restriction of a minimal length. I think it takes some time getting used to. We need to know this. I think this is an important feature of space. And I think almost everyone, still to this day, believe that space is continuous. And of course then, we can use Newtonian coordinates, Cartesian coordinates, Galilean idea of the Earth as being to the side of the Sun in the solar system and so forth. It changes everything. We are so used to think that we can just use space as a canvas and the canvas doesn't mean anything. That it's completely nonsensical, that it doesn't have any. Well, this is previously done by Derrida, showing that the blank space is not unnecessary, it's part of reality. We spoke in the lecture before about parenthesis being unnecessary. I think this whole idea of exclusion comes from the miscalculated misconception stemming from the Greek that time and space are not discrete units, and that we can use them instead of what they are as what we think is a tool. But even the tool has to follow the idea of discreteness. It does distorts everything, and it will lead your thinking into completely wrong ways, no matter what you do. This is not restricted to physics. My experience of humaniora, especially linguistics and logics, they all think that the space doesn't matter and that the time that to do logic doesn't matter either. They become trapped in a fantasy world, I realize now. And here I say thank you very much and have a very pleasant morning still. Bye bye for now.